In this video, we'll continue working with applications of properties of quadratic function. Let's say we would like to find the minimum product of two numbers whose difference is 6. What are these numbers? To answer these questions, assume that our numbers are called x and y. So let x and y be the two numbers. Without losing generality, we can also assume that, for example, x is larger than y. Obviously, these two numbers are not equal because they differ by 6, right? So let's record the information that we have given. We're looking for the product, so we're going to investigate the product, call it P, of x and y, knowing that the difference of these two numbers is 6. That means the larger number x minus the smaller number y is equal to 6. This equation allows us to change the product of the two numbers into an expression in one variable. For example, we could solve this equation for x, which gives us x equals 6 plus y. Now we can replace the x in the above product by expression in terms of y, 6 plus y. So let's plug in this expression here. We end up with the product. Instead of x, we have 6 plus y, and then times y. So our product is actually a function of one variable, function of y. And as you see, this is a quadratic function. Its graph is a parabola. Let's see how this parabola looks like. Let's draw a system of coordinates. On the horizontal axis, we'll have y, and on the vertical, p of y, the product, right? Now, if our parabola is given in a factored form like this, it's easy to find the roots of it. So the roots are, from this bracket, y should be -6 in order to make it 0, and this factor gives us 0. We have two roots, -6 and 0. Let's plot them. Let's say -6 is somewhere there and 0 over here, right? So those are the 2 points that belong to our parabola. Since the leading coefficient, the coefficient by y squared, is positive, the parabola will have arms up. That means that its vertex will happen exactly halfway between these two roots, that is, at the point -3. So we already know that y minimum, the first coordinate of the vertex, is equal to -3. Therefore, the second coordinate, p minimum, the minimum product, is equal to the value of the function p at the point -3. So let's plug in the -3 to our expression. It is 6 minus 3 times -3. This value is 3 times -3, it's -9. So we know that the vertex of our parabola in this system of coordinates is -3, -9. Let's say -9 is somewhere here. So that will be our vertex, and the parabola goes somehow like this. Okay, so we are nearly ready to give the answer. We know the minimum product, it is -9. And what are the two numbers? Well, one number is -3. What's the other number? X is equal to 6 plus y. So x, that gives the minimum product, is equal to 6 minus 3, which is 3. Okay, now we have all information to give the final answer. The minimum product is -9, and the numbers are -3 and 3. Let's see another application problem. A rancher needs to enclose two adjacent rectangular corrals, one for sheep and one for cattle. If a river forms one side of the corrals and 180 yards of fencing is available, what is the largest total area that can be enclosed? And here we have a diagram. The river on one side, and we have two adjacent corrals. So, what are we after? Well, we want the largest total area that can be enclosed. The area of a rectangle is its width times length. So let the width of the corrals be x yards. This will be x, therefore this is x and this is x. Since we know that the total available fencing is 180 yards, we can figure out expression for the length of those two corrals in terms of x. 180 yards is used to build 3 width, 3 times x, and 1 length, right? Over here, because the other length is formed by the river. So we can solve this equation for L, which gives us 180 minus 3x, right? This way we express the length of the rectangle in terms of x, the width. It is 180 minus 3 times x. Okay, now we are ready to build the function of area. The area as a function of one variable. Which variable? The x variable, right? So a of x is the product of the width, which is x, times the length, which is this expression. So 180 minus 3x. That's our area function. It is a parabola, and this time the leading coefficient of this parabola is negative, so we'll expect an upside down parabola. Let's sketch a system of coordinates with the horizontal axis being x and the vertical axis a of x. Okay, we want to find the largest area, so we're really looking for the vertex of this parabola. Again, since our parabola is already given in a factored form, there is no need to multiply through this bracket. It's easier to look at the roots, which are 0 from the first factor and 180 over 3, which is 60, from the second factor. Similarly as in the previous example, we can use those roots to figure out where's the vertex. So the first root is 0, the second root is 60. Let's say here the first coordinate of the vertex is exactly half away, so it is at 30. That tells us that x that produces the largest area, x maximum, is equal to 30. Therefore, the largest area, a maximum, is the value of this function at the point 30, isn't it? So let's calculate it. That will be 30 times 180 minus 3 times 30. That gives us 30 times 180 minus 90, that's another 90. Altogether 27 and 2 zeros, 2700. Since this is area, it will be in yards square. So this time the question asks for the largest area. It doesn't really ask for the dimensions of those corals, even though we actually have got them now, because the x that produces the maximum area is 30, and this expression 130 minus 3x gives us exactly 90. So the dimensions are 30 by 90. However, the question only asks about the largest area. So we're really after the second coordinate of the vertex of this parabola. Let's say 2700 is somewhere here on our sketch. So that will be our vertex, and the parabola goes somehow like this. Okay, so now we are ready to give the final answer. The rancher can enclose 2700 square yards of the area. Finally, the last example. It's about a trip to a resort. A charter bus company charges a fare of $48 per person, plus $2 per person for each unsold seat on the bus. If the bus has 42 seats, and X represents the number of unsold seats, find the following. First, we need to find the function r of x that describes the total revenue from the trip, and we know that revenue in this case will be the number of people going for the trip times the price per ticket. So what is the number of people that go for the trip if X tickets were not sold? Well, that's 42 because it's 42 available places and X were unsold. So 42 minus X, that's the number of people that actually went for the trip, right? And now we need to multiply this number of people by the price per ticket. Each person normally would pay $48, but since some people didn't go for the trip, this price will be increased by $2 per person for each unsold seat. So if one seat was unsold, the price will be $48 plus $2. If two seats were unsold, the price per each person will be $48 plus 2 times 2, which is $4, and so on. Generally, the price will be $48, the base price, plus 2 times the number of unsold seats, 2 times x. So 48 plus 2 times x. That's the cost of each ticket. Okay, so our function revenue with respect to x is given by this formula. Now we want to graph this function. Again, we could graph it in different ways. We could multiply those brackets through, find the vertex, and graph similarly as in the previous video. Or we could take advantage of this factored form, find the roots, which are easy to get. From the first bracket, the first root is 42, and from the second bracket, the root is 48 divided by -2, so it's -24. Okay, let's plot those roots. But before we do that, we need to establish certain scale that will be useful for us. So since the numbers are pretty high, 1 square must represent more than 1 unit, right? Let's assume that 1 square represents 10 units. So that will be 40, and that will be -20. We're going to estimate 42 as approximately this point, and -24 as approximately that point. So those are the 2 points that belong to our parabola. What about opening of our parabola? Well, the leading coefficient comes from multiplying the x terms, right? So the leading coefficient is negative. Therefore, the parabola goes upside down like this. That tells us that the vertex is the maximum point. And to find the first coordinate of this vertex, it's enough to take the average of these two roots, halfway between -24 and 42. So, x maximum, the first coordinate of the vertex, is 42 plus -24 over 2. That gives us 9. And 9 is positioned somewhere here. That's the midpoint, right? Now, to figure out the maximum revenue, we need to evaluate our function r, that will be the maximum value, at the point 9. So we go 42 minus 9 times 48 plus 2 times 9. Okay, that gives us 33 times 66, which is 2,178, and that's in dollars, right? That's the maximum revenue for the strip. Okay, let's finish our graph. Since we need to be able to place the 2,000 something on the vertical axis, let's assume a scale in which 2 squares will represent 1,000. So that will be 2,000, and 2,178 is approximately here. Okay, so that will be an approximation of our vertex, and our parabola goes somehow like this. Okay, so we actually answered all those questions. We have the number of unsold seats that produces the maximum revenue. This is 9. And we have the maximum revenue. That's our maximum revenue, right? So how many people should go for the trip for the maximum revenue? 42 minus 9. We can say the highest revenue is attained when 42 minus 9, which is 33 people, go on the trip. As we see, quadratic function can be very useful in problems like this, where we look for extreme values. Such problems are often referred to as optimization problems.